Okay, so we've been talking about colligative properties, solutions, and the whole idea, again, sort of behind colligative properties, is really the idea of in a solution, we really have a solute dissolved in a solvent. And that's basically what makes up a solution is that presence of the solute, obviously, in the solvent. Now, the presence of that solute really does sort of change some properties here of the solvent by itself, as we sort of talked about last time. Essentially, it kind of gets in the way, and it gets in the way of sort of normal processes that normally would occur if obviously this solute was not dissolved in the solvent. So, for example, freezing of a solution, if you have a solvent by itself, there's really nothing sort of in the way of that process as those guys come together. Um, if you have just, say, solvent molecules in there, they're able to really, as they lose energy, sort of come together in sort of the solid form. In a solution, though, if the red guys are your solvent molecules and your blue guys here are your solute molecules. There are now other things in the way that, again, sort of gets in the way of these guys sort of coming together and freezing. And it ends up, as we talked about, freezing point depression. It actually lowers the freezing point in a solution rather than just the solvent by itself. Same thing happens again in sort of the normal process of heating something and boiling something. Again, just the solvent by itself, fairly has a straight sort of path out of the solution or the solvent or the beaker, I guess. Again, in a situation where we have both solute and solvent sort of particles in there, again, there's a lot more sort of obstacles, if you will, as these guys try to sort of escape the solution. They got to kind of go around. It takes a lot more sort of energy to do that. The result of that is we end up seeing that the boiling point actually starts to elevate in that particular case. So, really, the presence of the solute and colligative properties are really based on sort of how much particles are dissolved in the solution. It has a bigger effect on sort of those properties. We also talk about vapor pressure as well. Um, has a bigger effect on those properties, and the more particles that you have dissolved in there, and that just makes sense. Again, the more particles you have dissolved in there, the more sort of obstacles to these kind of normal processes that occur for the solvent. And we saw some different sort of formulas where we can look at things like freezing point, boiling point, vapor pressure lowering. So, for example, two main ones that we see a lot is looking at the change in freezing point. Temperature is the Kf times the M. Again, that is, as we talked about, the change in freezing point temperature. That is the basically freezing point constant. And that is our molality, which again is our moles per kilogram. Remember, a couple key things on this is the Kf. The Kf is not from the solution. So again, as we talked about last time, sometimes people really struggle with that aspect of it. They go to a table and go, I can't find the solution I'm dealing with. And that's because you won't find the solution, as we talked about. You will find the solvent. So the Kf is all about the solvent. And remember that although many times, many times the solvent is water, it's not always water in 100% of the time. So then, that brings up what we'd also talked about, that if it is not water as your solvent, a couple of things you do need to make sure of. You need to obviously get the right Kf or your Kb value, but you also need to think about the correct freezing point temperature and boiling point temperature, because that's helpful, obviously, in their calculations. We saw one with our boiling point, which was pretty much identical in terms of the formula. Our change in the temperature of the boiling point is our Kb times our molality. Again, this pretty much is the same thing. That is the change in boiling point temperature there. And again, change in the boiling point temperature. Our boiling point constant also based on the solvent. And again, our M, which is our molality, which is moles per kilogram. Now, when we talked about this is freezing point depression, which means basically the freezing point goes down, and it goes down in comparison to the solvent by itself. So if water was your solvent, again, it would freeze normally at 0 degrees. If you had a solution that water was the solvent and you dissolve some stuff in it, you would find that the freezing point of that solution would go below 7 degrees, or 0 degrees, 7 degrees. The boiling point is boiling point elevation. So we see that the boiling point here actually does increase, and it does go up. So same idea here. If you're sort of using water as your solvent, the normal boiling point is 100 degrees Celsius. And again, if you had something dissolved in there that water was your solvent, you would expect to see it actually sort of increase higher than 100 degrees Celsius. So when we do these things, remember the couple important relationships, the change in the freezing point temperature. Because the freezing point lowers, this is the temperature of the solvent minus the temperature of the solution. While over here, the change in the boiling point, again, because it elevates for the solution, is the temperature of the solution minus the temperature of the solvent. So that, again, as we talked about, are very important aspects of those calculations that will get you sort of the right sign, if you will, get you the right either multiplying or not multiplying, adding or subtracting sort of correctly here. We also talked about osmotic pressure. Osmotic pressure, again, sort of where we left off on, is the idea that, when you have a membrane, it sort of separates two sides. Say we have salt water on one side, regular water over here, pure water on the other side. The process of osmosis moves from a lower concentration to a higher concentration. So the process of osmosis will cause basically the water molecules to go across an effort to dilute down the more concentrated salt water. At some point, that process will stop when it hits really atmospheric pressure, exerting back down on it. And that's what's known as the osmotic pressure, that sort of stoppage of the flow of more solvent molecules across a membrane. You could calculate the osmotic pressure through some equation such as this. And again, that is the osmotic pressure. And this is really, as we talked about, think where we kind of ended up is just a fancy version of PV equals nRT, where we divide V to the other side. P is nRT divided by V. Again, N over V here is moles per liter, which is where molarity comes from. So, that is sort of how we get down to that equation. So if you want to think about osmotic pressure, really just an ideal gas law, basically. And again, obviously that means that we need to be careful with those units like we talked about at the end last time. The same normal units that we use in the ideal gas law is what you need to use here. Any questions on any of that stuff we talked about last time? I think we left off there at a example here. What is the molar mass of a protein if 5.86 milligrams per 10 milliliters gives an osmotic pressure of 2.45 torr at 25 degrees Celsius? So if we were going to sort of do this, we want to think about, again, molar mass like we kind of saw in one of those earlier problems. This is ultimately what we're looking for, which means we're looking for grams per mole. So we do want to think about, do we have sort of any of those numbers up front? And if we think about just straight out reading here, we have 5.87 milligrams. Although it's not grams, we can convert easily milligrams into grams. So we do have the top part. We think about the rest of the information sort of given to us. We have 10 milliliters, which is a volume. We have an osmotic pressure, which is obviously a pressure. We have this guy, which is a temperature. And if we think about, since really osmotic pressure is nothing more than the ideal gas law, we have pressure, we have temperature, we have volume. We always obviously have R. That means that the only thing we really don't have from the ideal gas law is moles. And that's actually what we're interested in, because that would be the bottom part here. So really in this case, we just got to do a conversion of our milligrams into grams. We then need to follow it up with basically using the ideal gas law, excuse me, using the ideal gas law and solving for moles. So why don't we do that here? So we'll start with our 5.8 milligrams, 5.87 milligrams, I think. There we go. 5.87 milligrams. There's 1,000 milligrams in a gram, right? Like 1,000 milliliters in a liter, right? It's kind of the same conversion. And if we do that, 5.87 divided by 1,000, going to get us 5.87 times 10 to the minus 3 grams. So right there, by that conversion, we now have the top part that we need. Now we're going to go into our ideal gas law and solve for N. N would equal PV over RT. So remember that we do need to be careful of units. So obviously we have 10 milliliters, and 10 milliliters, again, 1,000 milliliters in a liter. That will get us 10 divided by 1,000, 0.01 liters. So now we're in the right units for our volume. Our pressure here is not in the right units, so we do need to convert that. So that's a 2.5 torr. Remember that it is 760 torr in an atmosphere. And if we do that conversion there, divided by 760, gets us 0.00322, we'll call it. 0.00322 atmospheres. So that's good. And lastly, obviously, our temperature here needs to do a little conversion. So that's a 273 plus our 25. 298 Kelvin. So now we got everybody in the right units, and we can put that in. So that's 0.00322 atmospheres. Our volume, 0.01 liters. Our R, which obviously we always have. So, and lastly here, our temperature of 298. Everybody's going to cancel out except for our moles, which is good. And that gets us that times that divided by this and divided by that. That gives us a, let's see here. We'll go with a 1.32, 1.32 times 10 to the minus 6 moles. So 1.32. And again, that is now the bottom part that we need. So pretty much we have everything that we need now to calculate our molar mass. We're simply going to divide those two numbers. So we'll do a 5.87 times 10 to the minus 3 grams divided by our 1.32 times 10 to the minus 6 moles. And that will yield us approximately 4.45 times 10 to the 3 And again, the units don't cancel, so that is grams per mole, which would be our molar mass here. Any questions on that? So this is, pretty identical to what we talked about in sort of the gas chapter there, where we talked about calculating the molar mass of a gas, kind of using the ideal gas law, or really that formula as well. Any questions on that calculation there? All right, why don't you give one a go here and see what you come up with. So why don't you give this one a go? What is the molar mass of a lysozyme? That is 0.075 grams and 100 milliliters. Gives an osmotic pressure of 1.32 times 10 to the minus 3 at 25 degrees Celsius. Okay, let's take a look at this one here. So same sort of approach. We're looking for the molar mass. So much like the previous example there, obviously grams per mole is what we're looking at. Right here, in this case, it's actually in grams, so we're good to go on the top part. Now, the rest of it, just like we did before, going to really come from sort of our gas law. So here's our volume, which obviously does need to be converted to liters, as we already know. Here's our pressure, which is actually in atmosphere, so it's actually good to go. And that is our temperature, which obviously needs to be converted into Kelvin in this particular case. So basically, as we did before, we could go with our PV equals nRT, or you could use the fancy formula of it if you like. We're going to solve for n as we have everything else sort of given to us. So we're going to put in our numbers, which is 1.32 times 10 to the minus 3 atmospheres. Our volume, which again, we did convert to liters, so everything cancels out correctly, because again, we are still using our normal gas constant, and that is liters, atmosphere, Kelvin, mole, and our temperature here converted into Kelvin. That gets us a 1.32 to the minus 3 times 0.1 divided by 0.08206 and divided by 298. Gives us a lot of zeros to count, but it looks like 5.40 times 10 to the minus 6 moles. Again, we already have the grams, so our grams per mole here for our molar mass would be our 0.0750 grams divided by our moles here. And that does yield us for this guy a fairly big molar mass of 1.39 times 10 to the 4, positive 4 grams per mole. Any questions on this calculation here? Obviously, this is an application of osmotic pressure. You obviously can, as we talked about last time, just go right into the formula and solve for something like the actual pressure, which would be sort of the osmotic pressure in that particular case. All right, any questions so far on that there? All right, so what we're going to talk about now, and sort of, I guess, what we've talked about up to this point in terms of sort of colligative properties, is when we think about sort of the solute that we been talking about, we've been talking about really non-ionic solutes. And what I mean by that is up to this point, we've done non-ionic or covalent solutes. So if you look back on a lot of the sort of examples that we did before, it was like glycol and all that kind of stuff, which was basically a lot of like carbons, hydrogens, oxygens as like our solutes. And these guys, as we know, are going to be sort of covalently bonded. They're going to be sharing electrons. They're really not ionic compounds that we were dissolving in our solution, like glucose or something like that. So for example, when you have those type of particles that are non-ionic, when you take one particle of it and you put it in water, you basically get one particle. It basically dissolves as a whole thing, right? So kind of like those non-electrolytes, when they go for a swim, they do dissolve like sugar, but they do not break apart into ions or anything like that. So it's kind of like a one-for-one relationship. Now that's very different than if we took something that is an ionic solute and we dissolved it in the actual solution. So for example, if we took something like, say, sodium chloride, right, and we put it into water, when it goes into water, we get a sodium ion that's floating around and a chloride ion that's floating around. We actually now get not really a one-to-one, like one went in, one particle went in, one particle came out. In this case, we got one guy went in, but we actually get two particles that are now floating in that solution around with that solvent. You know, if we took something like, say, calcium chloride, also again, put it into water, we get a calcium ion, we get a couple of chlorides, right? We now have three particles that are basically floating around that solution. Remember that all of our sort of colligative properties are really based off of how many particles there are. And the more particles, again, the more sort of things in the way of those processes like boiling point, freezing point, that can occur. So to correct this, when we're dealing with sort of ionic solutes, like sodium chloride, calcium chloride, or whatever it may be, we use the von Hoff factor, and the von Hoff factor really takes into account that process where we have multiple particles basically going into solution. The measured von Hoff factor are usually less than the theoretical one, but in most cases, we can use the theoretical sort of value for it. And the von Hoff factor is basically what I is. And what we do with this I is essentially on all those sort of colligative property formulas that we just saw, mainly like the boiling point, freezing point one. So if you remember, the freezing point one was this. And our boiling point one was this. And again, you can apply this to other ones that we saw as well. We essentially insert I into that formula. And the I is basically put right there. You'll see I. So when we're dealing with ionic solutes, we need to make a slight adjustment to our sort of colligative property formulas by inserting that I into there to represent basically how many particles. So how you figure out I, again, you can basically use it based off of the formula. And off the formula here, sodium chloride, again, gives us two particles, which means in this case, I would equal 2. Calcium chloride, when it breaks apart, gives us 3 particles, which means I would equal 3 in this case. So you may be asking, why did we not sort of take into account I when we're dealing with these non-ionic sort of solutes? And the answer is really lies here, as we talked about. You do get a 1 particle kind of when it goes in for a swim, which technically means I is equal to 1, which basically means that that is basically KF times M without the 1 in there. So that's why we typically don't include the I in those formulas when we're doing non-ionic, because it's really equal to 1 and it basically just stays the same regardless. So how does this affect it? Well, let's think about sort of what is happening in sort of a I equals 1 situation versus 2 versus 3, for example. So let's just say, for example, we had a solution that had a molality of 2 molal, right? And we wanted to look at the freezing point, right, of this solution. So let's take a look. Let's say it was sodium chloride. So our sodium chloride, if we did our change in freezing point temperature, which would be I times KF times M, in this case, taking into account I, which would be 2 for sodium chloride, the KF 1.86 degrees Celsius per molality times my made up 2 molar If we do that for our sodium chloride solution, we end up with a change in temperature of 7.44 degrees Celsius. So a sodium chloride solution with this arrangement will actually freeze at not 0 degrees, but it will freeze at minus 7.44 degrees Celsius. What happens though if we did the exact same sort of setup though, but we looked at calcium chloride? So also ionic, we'll also say it's 2 molal as well. When we do our change in our freezing point temperature, it's going to actually equal now 3, because there's 3 particles that are there, our 1.86 degrees Celsius times M, and our made up 2M there. Again, those guys cancel, leaving us with degrees Celsius. We see we end up with a change in the temperature of about 11.16 degrees Celsius. So this guy will now freeze at probably somewhere near minus 11.16 degrees. The only difference is the number of particles that are dissolved in there. We see 3 is more particles than 2, so more things in the way, going to affect our freezing point by making it lower than it would if there was only 2, and obviously lower if it was a non-ionic compound, where you would technically just go, the change in the freezing point temperature would be 1.86 times 2 molar, as I would equal 1 in that particular case. And in this case, 1.86 times 2 gives us a 3.72 change in temperature as well. So you see in an ionic situation or something, you had a solution that was 2 molal, 3.72 would be the change in freezing point, or minus 3.72 if it was 0 degrees Celsius, if water was what we're dealing with. 7.44 it drops, and then it drops 11.16. So again, this illustrates to you the idea that really colligative properties are based off of the number of particles that are present, and the more particles present, the greater degree you're going to have an effect on, obviously, something like freezing point. Any questions on that there? So here's sort of a table illustrating sort of what we've been talking about. Non-electrolyte, really, I is 1. And again, that's why we don't necessarily kind of put it into those formulas that we used earlier on where we're using non-ionic. But again, here, sodium chloride breaks apart into 2 ions. Magnesium sulfate, also 2 ions. 3 ions for magnesium chloride, 1 magnesium, 2 chlorides, 2 potassiums, 1 sulfate, and 1 iron, 3 chlorines gives us 4. The actual measured experimentally, as you can see, are just slightly off of these numbers. In some cases, some are a little bit more than slightly off. But for textbook problems and stuff like that, you pretty much could do it based off of the format. So again, like it shows there, if you had iron 3 chloride, that means you have an iron 3 that goes in there and 3 chlorides. So 3 and 1 is an I that's equal to 4 in this case, and you'd be safe for your calculations. Any questions on that there? All right, so why don't you take a look at one and see what you come up with here. What is the measured von Hoff factor? So you're actually looking for I in this case. If we have a 0.05 molality calcium chloride, freezing point of minus 0.27 degrees Celsius, and a reminder that the Kf here is 1.86 degrees Celsius per molality. So take a second and see what you come up with. Okay, so let's take a look here and see what we're dealing with. So first off here, we're looking for the von Hoff factor. The reason we need it is our solute here is, we got there, our solute is calcium chloride, which is ionic. So again, because that is ionic, we do need the I factor. Again, not a major difference in the formula other than we do just need to kind of insert the I into the formula that we've used previously, and everything else pretty much the same. So it is an ionic compound, which means we could pretty safely assume that the solvent here is going to be water, right? And that's because we have our ion dipole interaction that's going to happen. Pretty much ionic things and water are soluble, so that's a pretty safe assumption. And again, that is why we would go to our sort of table there and find the Kf value there for water. So we do have the Kf value. They did give us the molality where we are actually looking for I. We need the change in freezing point temperature. Again, a reminder here, we got to be careful of certain things. This right here is not the change in freezing point temperature. This is the temperature of the solution. So remember that because this is freezing point depression, the change in the freezing point is going to be the temperature where the solvent freezes minus the temperature of the solution. And again, because the solvent is water, the normal freezing point for this guy would be 0 degrees Celsius. That means that the change in the freezing point temperature would be 0 degrees Celsius minus or minus 0.27 degrees Celsius. And that is really how we get rid of our negative sign here, is by using that relationship, because the change in temperature here is 0.27 degrees Celsius. Again, not negative 0.27 degrees Celsius. Any questions on that? Now, again, you may be saying, can I, just kind of get rid of the sign there, and use it? Well, the answer is it might be okay if, again, the solvent's water. If the solvent's not water, then this freezing point may actually be a different number than 0, which means obviously your number here would change as well. So again, why it's really important to make sure you're using the correct freezing point or boiling point for your solvent, as again, it's not always going to be 0 in that particular case. Yeah, we did get water as our solvent because of two things. Really, again, it fairly almost safe bet a lot of times that it says aqueous. That essentially applies water as your solvent. But more importantly as well, when we look at this guy, it's ionic. And ionic things are soluble in water. And that's a pretty safe bet that it's going to be water as your solvent in that particular case. Other questions on that? So now that we have the change in the freezing point temperature, which again is this guy here, we could do a little rearranging there and actually solve for I in this case, which is unusual, but we'll solve for I, which is the change in freezing point temperature divided by Kf and our little m there. That is going to be our 0.27, so we don't get our negative number. We did that correction there. Our Kf being our 1.86. And our M here being 0.05, and doing all that good stuff there. We got 0.27, 1.86, 0.05. Looking like we get something like an I value of 2.9, basically. Any questions on that there? So this information here was technically, from an experiment somebody did, technically speaking, since it said measured and stuff like that. And experimentally, they found that the von Hoff factor was 2.9. Again, if you just took the formula of calcium chloride like we did on the previous page, when it breaks apart calcium plus 2 chlorides, we would basically estimate that the I value would be 3, which, as you can see, is very close here to sort of the experimentally found value, which is why we can pretty much for most problems just take the formula and just use the formula, how it breaks apart into their individual ions, and just call that your I factor. Any question on the von Hoff factor and sort of how it plays into the formulas that we used previously? Basically just kind of insert an I, on all those kind of formulas we saw before, where we had the equals part, you basically insert the I onto this side of it and for ionic sort of compounds, and you can take care of it. Any questions on that there? Okay, so obviously, as we've talked about, you need to be able to do freezing point, boiling point, we do osmotic pressure, vapor pressure lowering, again, and excuse me, and non-ionic and ionic sort of situations to be able to do it correctly. We're going to finish up talking about a few more properties of solutions here. They agree with us, so that's good. All right. So a couple of things about solutions. As we've been talking about before a little bit here, there's a semi-permeable membrane. And it's basically, you know, a membrane that allows certain molecules to pass through and sort of prevent other ones from passing through, you know, like cell membranes and stuff like that. But, you know, if you take like a membrane and, you know, if you super zoomed in, you know, there's certain like sizes or holes, if you will, that allow, you know, small little guys, perhaps no problem, can kind of go through those to the other side. But, you know, you try to get something a little bit too big, is going to be a no-go. It's not going to be able to fit in there. So it sort of prevents those things from flowing from one side to the next. Sort of excluded by size, basically. When we talk about certain types of solutions like colloids, or I guess colloids not really a solution per se, but colloids are much larger than a solute particle in a solution. And these are really large molecules like proteins or groups of molecules or ions that are together. They are homogeneous, which means that, you know, kind of like a homogeneous mixture, they mix, they're the same throughout, which means that they really do not separate or settle out because they're homogeneous. They are small enough to pass through filters, but they're kind of too large to pass through membranes. Suspensions, on the other hand, are heterogeneous, non-uniform mixtures. So again, very much like a heterogeneous mixture, where if you think about what that means, when you look at it, you see these different phases for sure. And same idea here, suspension is something that's sometimes large enough that you can see it with your naked eye. Because they're kind of non-uniform, really not great things that mix together. They are trapped by filters and membranes, so they really can't go through much. You know, for example, if you take like sand or something, that's something that you can see. It's got a lot of stuff in sand, and obviously if you try to pass the sand through a filter or a piece of filter paper, it's just going to get stuck on the filter paper. Here's sort of a zoomed in look at a semi-permeable membrane here in the middle. And again, you could kind of see that there are channels there, or holes, however you want to kind of look at it. And again, it allows these sort of water molecules, which in this picture are small enough to kind of go, really be passed back and forth through here as you kind of go through here. But obviously, as you can see there, when you got something like these little larger sort of proteins in there, like this guy, you know, it can't really make its way through there. It's going to get stuck as it tries to get through there. There's this guy over here, you know, again, a little too large to get through there as well. So again, going to allow these sort of smaller guys to pass through. So sort of limiting things based on sort of size, and allow certain things to sort of pass through, like our cell membranes, you know, allow certain things to kind of filter in and filter out in your body. Here's sort of an example of those other things here. We have our solution, which really doesn't settle our colloids, but again, our settling that we see here with our suspension, kind of like, you know, like maybe medicine or things like that. Sometimes, you know, it comes as a suspension where you got to kind of mix it up really good, right? And do a lot of mixing to get it really mixed. But then, right, if you leave it, you know, you start to see certain parts of that medicine or something like settle down to the bottom. And that's again like a suspension. Here, if we try to put it through a filter paper, you can see our suspension getting caught, but our solution or colloids going through the filter paper. And this is like a membrane here, kind of like a dialysis bag. Again, only really allowing kind of those smaller solution molecules to basically exit in and sort of out of the bag in that particular case. So that brings us to osmosis, and osmosis, as I sort of alluded to earlier, is sort of the natural process where basically solvent water molecules move through a membrane from an area of lower concentration to an area of higher concentration. So the idea here is it's sort of trying to dilute down the more concentrated one. So this is sort of what we were talking about earlier when we were talking about sort of one side had the salt water. Obviously, if it's salt water, it has like sodium chloride or something dissolved in it, so it has a higher concentration than just pure water over here. And again, water would flow across the membrane, again, in an effort to sort of dilute down the salt water on the other side. Again, at some point, it is going to sort of be blocked there by our osmotic pressure, which is going to stop that constant flow of solvent molecules across that membrane. Pure water has no osmotic pressure, and it's because it basically has nothing dissolved in it, right? So in order for it to do that, it has to have some type of concentration or something to be dissolved in it. Another measure of sort of this is what is sometimes referred to as osmolarity. And sometimes referred to as osmolarity or osmol. And osmolarity is really like calculated from I times the molarity, really. So, you know, if we had again, a 2 molar sodium chloride solution versus a 2 molar calcium chloride solution, again, they both really have kind of the same molarity. And again, we're going to go big M on these, so molarity here. That's big molarity. They both have the same molarity, so you might assume that they perhaps would sort of exerts the same sort of osmotic pressure and stuff like that. But again, if we do our sort of calculation, we already figured out in the last one, I is 2 here, I is 3. So if we put it into here, we see for sodium chloride, it would be 2 times 2 molar, gives us a 4 osmolarity. And if we did that for our calcium chloride, it would be 3 times our 2 molar, gives us our 6 osmolarity. And again, here we can see greater osmotic pressure sort of being exerted here by our calcium chloride than our sodium chloride. Again, back to the idea of, you know, pretty much everything is based on how many particles are present in a particular solution. Again, water having no osmotic pressure because really has nothing dissolved in it if it's pure water. Here again, just a way of showing that brine is basically kind of a salt type solution. So this definitely is more concentrated over here. The pure water is less concentrated. The water is going to flow across the membrane here, as you can see, in an effort to basically dilute it. At some point, again, that flow is going to be stopped, and that's our osmotic pressure. Again, the difference here, as you can see, our osmotic pressure, which was our formula that we saw earlier there, which again is basically just the ideal gas law. Now, what is sort of reverse osmosis? Well, reverse osmosis is you basically apply a pressure that is greater than the osmotic pressure. What that's going to do is basically is force everybody back this way. And as you force everybody back this way in terms of your solvent molecules, like your water, for example, you have a lot of good filters sort of happening there. It'll catch all the brine and junk that you really don't want. And then over here, you will have basically just the water basically coming back out. So it's almost like pushing it through, like a syringe, for example, that has like content in it, pushing it through the filter and all that's going to catch all the junk that you don't want, and sort of coming out the bottom will be kind of that pure water. Any questions on that there? So that leads us to three ways that sometimes solutions are described as either isotonic, hypotonic, or hypertonic solutions. So let's talk a little bit about isotonic solutions. Isotonic solutions basically exert the same osmotic pressure as body fluids. So that's why typically IV fluids that we use are usually isotonic solutions, because obviously if you're getting an IV, you're probably not in good shape. So you don't want to do anything that's going to kind of screw up your cells. What do we consider isotonic solutions? Well, for the most part, 0.9% mass to volume sodium chloride, sometimes just referred to as a saline solution, or really any ionic sort of compound that's 0.9% is basically considered isotonic solution. 5% glucose are also isotonic solutions. So these two solutions are isotonic, and those are important numbers to remember because those are bases of isotonic solutions. So if we were to put, the obligatory sort of red blood cell there into an isotonic solution, what we would get is basically equal flow of solution in and outside of the cell acting sort of like as a membrane, right? So again, water will sort of flow in and outside. I would say water, but I guess solution, I guess, will flow in and outside of the cell pretty equally because there's the same osmotic pressure on the outside as the inside of the cell, and nothing bad happens. Now, if we were to look at a hypotonic solution, hypo means lower than. So this is a solution that is lower in concentration than, say, the red blood cell. So for example, if we did that, we take our same sort of red blood cell and put it into a hypotonic solution. What's going to happen is inside the cell is actually more concentrated than the outside where the solution is. And remember that osmosis is the flow from lower concentration to higher concentration. So what will happen in that case is all those sort of outside solution will basically make a run into the cell. And when it does, it's going to cause the cell to start to swell because it's taking in all this extra sort of water or solution and possibly burst, which is known as hemolysis, which obviously is not a very good situation. A hypertonic solution, hyper means greater than, means that when we put it into for example, a red blood cell into a hypertonic solution, that means that outside of the cell is more concentrated than inside the cell. So in a hypertonic solution, take our good, happy red blood cell, put it into a hypertonic solution. Again, outside more concentrated than inside. The red blood cell is going to go, wait a sec, I need to help dilute everybody on the outside. So basically all of the fluid from the cell is going to start to rush out of the cell. And when it does, it's going to cause the cell to start to shrink and go through a process known as crenation, which obviously is not a good thing either. So isotonic solutions, 0.9% sodium chloride, some type of ionic compound that's 0.9%, again, sometimes referred to as saline. A 5% glucose considered isotonic, nothing bad happens in that case. So if we look at some pictures of this, a little better pictures here, this again is our isotonic solution. So we got nice equal flow in and out of the cell, kind of like a good old donut. We have our hypotonic solution where all the water and stuff's going to come out of the cell to try to dilute the outside, making like a donut hole. And then we have our hypotonic solution where everybody's running inside to the cell, going to make this thing start to swell and possibly burst like your jelly donut, right? So we can relate these to donuts, basically. It is morning time, why not? So why don't you give it a try here? Let's say we did take a red blood cell, and let's say we put it into We'll go with 5% sodium chloride. Let's go with a 3% glucose solution. Let's go with our good friend water, pure water. And you decide, are these solutions isotonic, hypotonic, hypertonic? And what will happen to these cells? Will it nothing happen? Will it shrink? Will it burst? We'll go through hemolysis and so forth. Our crenation should take a second or two here and decide. See, so first off, we should kind of know what isotonic is. So remember that we talked about if it's an isotonic solution, that means that it is either going to be 0.9% sodium chloride, or again, some type of other ionic compound, or 5% glucose. So when we look at our first solution here, 5% sodium chloride, it is as simple as 5% is larger than 0.9%. That means that that is greater than, and that should be a hypertonic solution. And we should know that what will happen in that hypertonic solution is, obviously, if we put our red blood cell in there, our hyper, outside is more concentrated than inside. We will start to see all the fluid from the cell basically rush out in an effort to kind of dilute the outside, and we will see shrinking occurring. And that again is what is known as crenation, which would be this situation right here. Any questions on that one there? Now, if we look at 3% glucose, again, comparing it to our isotonic solution, 3 is less than 5, which means it's less than, that this would be a hypotonic solution in this particular case. So 5% in the first one, just so we're clear, the question was, where's the sort of the 5% we're talking about? It's on the outside of the solution. It's in the solution, basically. So I'll just color it this red part here, the solution here, not the red blood cell, but the red part there was a 5% sodium chloride solution, basically. You toss the red blood cell into. So just like here, we would be tossing that red blood cell into the solution on the outside, which would be 3% glucose. Other questions on that? So because this is hypotonic, that means on the outside of the cell, it is 3% glucose. What's going to happen is outside of the cell is less concentrated than inside the cell in this case. So in this case, all that 3% glucose solution is going to go, okay, we need to kind of move into the cell. And when it moves into the cell, it's going to cause the cell to start to swell and burst in this case. And that's known as hemolysis in this particular case. And we will get that kind of swelling and bursting sort of condition. Any questions on that one here? Then lastly here, we're putting our red blood cell into water. And again, on the outside here, obviously in the solution is the water. And you may say, well, it's water, so obviously it's safe, right? Water is pretty safe. And in this case, not so much. Water has no osmotic pressure. And there's nothing really dissolved in water, which means actually the water on the outside is a hypotonic solution compared to the red blood cell, which means the outside is less concentrated than the inside. And that means that we are going to get everybody to flow into the cell, and it will start to swell and it will cause it to burst and go through hemolysis as well. We actually will get that situation occurring there. So sometimes people think, well, it's just water, right? So it should be safe. In this particular case, it would not be good to give yourself water there in an IV, again, because no osmotic pressure going to cause everything to rush into the cell and basically cause it to swell and burst. Any questions on how to identify those things? Okay, the last thing we're going to talk about here in this chapter is dialysis. Dialysis is a process similar to osmosis. It allows certain size molecules and ions, as well as solvent molecules, to pass through, but again, sort of retain large particles like colloids. Again, sort of like size exclusion, there's sort of holes that allow certain things to flow through. Here again, this is like a dialysis bag, for example. Again, going to allow those kind of smaller guys to really pass through. These really larger guys are going to be out of luck. They're going to find themselves still sort of in the bag as well, sort of like what our body does, right? It kind of filters out all the byproducts, our kidneys, we need dialysis and stuff like that, to filter out the waste products and stuff like that from your body and stuff like that. And that's essentially, sort of the same idea here. In the laboratory, we sometimes use dialysis in a process where we want to sort of equalize something. We could put it like a protein into a bag, and we know the protein won't really get out of that dialysis bag because it's too large. And what you could do is put it into an environment, maybe like a pH environment, maybe the correct sort of acidity or basic type environment, and let it kind of sit there for a while to sort of simulate the actual environment that protein would normally be in, and say like the body or something like that. So sort of a lab application of this sort of process. Any questions on any of that there? That should wrap up this chapter 10. And again, this is the last information that will be on the exam coming up this Monday on chapter 9 and chapter 10. Any questions on any of that stuff there? All right, then we will be off to the final chapter of the season here. Again, this is going to be our final chapter here, so that's good. We made it to the final chapter. Also a reminder, obviously, nothing from this chapter will be on the exam on Monday, but it will, some of this stuff will be on the exam on Thursday, which is your final exam. So again, not Monday material from this point on, but Thursday material, I guess, since we only got one more week here to go. So we're going to talk about chemical kinetics sort of in this chapter, and basically the idea of kinetics are in chemistry. Sometimes we talk about kind of two really big topics of chemistry, and that is thermodynamics, and that is really kinetics. And we don't really talk about thermodynamics in this class, but when you go into 200B, you talk about thermodynamics a little bit more. But thermodynamics deals with like the energy aspect, which, as we talked about throughout the semester here, they kind of took out of this class and put it into 200B. But about energy, and also about, really the idea of whether or not a reaction will take place. So oftentimes when we deal with thermodynamics, as you'll see in the next class, a lot of the questions that you're asked is a very simple question of, is this reaction spontaneous? And the answer is either kind of yes or no in a lot of cases. But there is something that some people sort of misunderstand when they sort of answer that question of, yes, the reaction is spontaneous. Sometimes when we think about something being sort of spontaneous, or we say a reaction is spontaneous, we sort of associate with it the idea of, well, it's spontaneous, so it's going to be fast. And when we talk about spontaneity sort of in thermodynamics, it has really nothing to do with how fast or even how slow a reaction takes place. If a reaction is spontaneous, what it really means is under those conditions, you would expect that reaction to actually take place. Now, that reaction could take place really, really fast, like a snap and boom, the reaction goes. Or it could be a reaction that takes a very, very long time to actually occur. But it will occur even if it takes a very, very long time. So it's really important, especially more so probably when you go to the next class. When you think about spontaneity, remember that just because a reaction is spontaneous, it doesn't necessarily mean that it occurs really fast. All that's really telling you is what it says there for thermodynamics is, does this reaction actually take place or not? When we talk about how fast or slow, for example, a reaction is taking place, that is basically what kinetics deals with. And that's what we're going to talk about in this chapter is how sort of fast, or I guess on the opposite of that, sort of how slow a reaction, may take place. And when we're talking about sort of how fast or slow something takes place, we oftentimes deal with what is sometimes referred to as a reaction rate. And what that means in terms of sort of reactions is when we're looking at either a reactant or a product, we're looking really on how its concentration is changing with time. And that's why we see the units for reaction rate a lot of times as molarity over seconds. So this is molarity, which is our moles per liter over seconds, which is basically how fast something is changing per time, right? So, if it's 2 molar seconds, it's changing 2 molarity every second, basically. So it gives you an idea how fast or slow something is changing. We can look at a reaction such as this one here, where the arrow kind of got eaten there by these things. So I'll just rewrite it here a little bit better. A going to B. And we could write what is sometimes referred to as a rate expression, which are these guys here. And these rate expressions allows us to basically make that identification of, how fast something is changing over a period of time. So if we look A, which is a reactant, we could say that the rate is equal to, and there is a negative sign, so I'll make it bigger here. There is a negative sign there. Negative, the change in the concentration. So when we see those brackets represent concentration. And usually, if I spell that right, concentration. And those brackets usually refer to molarity is usually what we're talking about when we see those brackets. So that's the change in concentration of A over the change in time. We could also write a rate expression for our product over here, that the rate is equal to the change in concentration of B over the change in time. And I will circle this here and note that there is no negative on that one. So no negative here, but negative here, which is really important. And it's really important because typically when you calculate the rate of a reaction, that rate is usually a positive number. So that negative there for our reactants is really important, why we don't have it there for our products. Why is that? Well, if we would expect in this reaction, right, if it were to take place, that in order to make products, so in order for this reaction here to go from A to B, or for that process to occur, we would basically need to use our reactants, which means the concentration of our reactants should start to decrease. And at some point, we will start making some products, and the concentration of our products should be increasing with time. And that's why the negative is here to represent that. If we just look at some simple numbers as to why that is negative is needed, so let's just say A going to B, and we started with 4 molar of A to start with, and 0 molar of B because we have no products to start with. And when we were all done at the end here, we ended up with, say, 2 molar of A, and we'll go with, say, 3 molar of B just to make up numbers in this case. If we were to do this, and we'll just say that this all occurred within a time of 10 seconds, for example. If we were to calculate the rate expression for A, that would be the rate would be equal to minus the change in the concentration of A would be final minus initial. The final concentration of A is 2 minus the initial, which is 4, divided by 10 seconds, right? Now, regardless of whatever number you get, when you do the top guy there, actually we'll get the number here. 2 minus 4 gives you a minus 2 divided by 10, gives you a minus 0.2. The negative that you get when you do this subtraction times the negative that's up here gives you a positive 0.2 molar seconds as the rate that's happening. So because reactants are always decreasing with time, when you do the change in the concentration part, you will always get a negative number, which is why the negative on the outside turns it into a positive number, which is what the rate should always be. Same thing happens if we look at B. We could do the rate for B there is, again, no negative. So it's the change in concentration. Final concentration is 3. Initial concentration was 0 divided by our 10 seconds gives us 3 divided by 10 gives us, again, a positive 0.3 molar seconds, which again is a positive number for the rate. You don't need the negative for the products because the product should always be increasing with time, which means its final concentration should always be larger than where it started. Again, you need the negative there on the reactants because its final concentration should always be lower than its initial concentration. Any questions on that there? So how can we follow sort of how, the concentration is changing with time? We could actually follow it by really some processes that, we've seen before, but this is just visually what we're just talking about there. Again, if the A is the black circles here and our red, which is the red circles, which are a product, we can see at the start of the reaction, pretty much all black circles, all A's present. And as time starts ticking away here and as this reaction starts running, we start to see some disappearance of the black circles and appearance of the red circles, which indicates we're starting to make some B's here, right? Along with obviously our A's is getting less. Again, less A's, more B's, less A's, more B's. Again, as the reaction continues all the way towards the end of the reaction, wherever it may stop, again, we see a lot more B's here, right, than we do see A's that have developed. So again, we're seeing that progression of reactants going to products. We're seeing what we were just talking about, that the reactants are lowering in their concentration as they're being used up for that reaction to take place. Products are starting to increase. And we see that visually here on the graph. At the start, time 0, it's all about the reactants, 100%. Pretty much no products there. But as we start to use some of our reactants, we start making some of our products and we start to see some product formation sort of happening. And again, why we have the negative here for our reactant and this guy really no negative, kind of a positive sort of way for the increase there in our products being formed. So how can we kind of follow that concentration as I was sort of alluding to earlier? We could do a process very similar to sort of what was done in that, I think it was the Kool-Aid experiment. For example, if you do have a reaction where there's some type of color, so maybe a reactant makes a color, maybe a product makes a color, a lot of times reactants starting with color, we can follow the change in that color over time and really get our sort of kinetics information that we need. So for example, here, this is basically Br2, so it's got a color. Everybody on this side of the reaction is sort of colorless. So visually, just looking at this sort of beaker, if we were to do this reaction here and just let it sit on the tabletop there, we would see it go from this kind of reddish color to an orange color to a yellowish color to really no color at all, indicating that perhaps the reaction's over. We're on the product side at that point. But we could actually use something like a Spec 20, spectrophotometry, basically to follow what is happening here. What we know is, right, our good friend Beer's law there. A is equal to, for one version of it, BC, where A is absorbance, B is Beer's constant, and C is concentration. B sort of encompasses both the path length and the molar adsorptivity. So I think in ours it was like AABC or something like that. So we had an extra letter in there. But the idea here is basically if there's some type of color in the solution, right, we could shine a light source at a specific wavelength that is complementary to the color of the solution, right? And we could measure something like absorbance, right? And again, that is basically how much light gets absorbed by the solution versus what reaches the detector. And remember that the darker the color of the solution, the more absorbance value you would have. The lighter the color of the solution, the less absorbance value you would have. This graph over here should sort of look familiar to you as well. Remember, when we kind of use that, we need to kind of figure out where should we set the wavelength. And a reminder that, as I just mentioned, you know, again, sometimes people will miss this question because they're like, hey, the color is red. Why am I not setting it to the red wavelength? And remember that we set it to the complementary color to the light that of the solution, because that is what's being absorbed. And we can figure out where the maximum absorbance happens by doing a graph of absorbance versus different wavelength. That's kind of like what the what they call it, spectromaster guy did in that experiment where we did all the different sort of wavelength. And what we would want to choose, for example, in this example here, is a wavelength that matches really the peak. And again, I'll do a bad straight draw there. The peak there of that guy, because that's going to give us absorbance values when we run our solutions. We could get values all the way through, all the way up there. As opposed to if we messed it up and said, I just want to choose my wavelength over here, that's about all the absorbance we're going to get is like right there, which means that most of your samples, right, will be off of the scale. So absorbance is a very easy way to sort of follow the change in concentration over time. You basically take a bunch of absorbance values every second if you have a computer do it for you, every 5 seconds if you're doing it for yourself or something like that. But you can basically take an absorbance value of your reaction every so many period of time. And what we see is that the change in the concentration, for example, BR2 is proportional, that's what that means, to the change in the absorbance value, which means if we're looking at BR2, we know it is this really dark color, which means we should have a very high absorbance value. And if we have a high absorbance value, that means we should have a pretty high concentration of BR2, right? Because if you put that in, you're going to get a pretty high absorbance value. As this reaction progresses, it's getting lighter, this sort of value, which means we have less BR2 as time goes by. The absorbance value starts to drop. Even lighter, less BR2 present at that point, absorbance value drops, and obviously no color, so very little to none, probably BR2 at that point. That would allow you to figure out the absorbance value. You could do a graph or something like that to figure out what Beer's constant is, and you could actually rearrange this guy and solve for the concentration. So you can convert your absorbance values into concentration values. And now you have a very much way of going, okay, at the very beginning, based on this absorbance value, I had this concentration of BR2. And at like 5 seconds in, based on this absorbance value, it corresponds to this concentration of BR2. You know, at 100 seconds, I had basically this absorbance value, which maybe is close to 0. And you're like, I basically had none of the BR2 left. Any questions on how you could kind of use a very simple sort of process to follow sort of how things are changing over time? Now, for example, if we kind of look at this BR2 and we kind of look at a graph here of what's happening, we do see sort of a decrease in time. As time decreases, we again see that concentration of BR2 basically decrease. And we see the rate at 100 seconds is 2.96 times 10 to minus 5, not really important. The rate there at 200 seconds, and then at a 300 second sort of area there is that. We can figure out the rate instantaneously by taking the slope of the tangent, which we won't really do that calculation here. But there's two types of rates that we sometimes talk about. A lot of times we deal with really sort of the average rate of the overall reaction. And there's the average rate, and there's sort of an instantaneous rate. And one way you could kind of think about those things is like, for example, if you're driving somewhere, say you were driving from here to, say, Arizona or something in your car. And along the way, you may be driving 55 miles an hour, 65 miles an hour, 70 miles an hour out in Palm Springs, maybe 75 miles an hour when you cross the border there in Arizona, maybe 85 if you're going a little too fast at some periods of time. But along your trip, you know, you're maybe driving at these different sort of speeds. And, you know, if you take just like a snapshot, like, hey, you just crossed the border there, and from the border 5 miles in, you know, you're driving maybe 75 miles an hour. But before that, maybe you're driving 65 miles an hour, you know, the 12 seconds before you got across the border or whatever it may be. So, you know, those little pockets of time on your trip there, every so often, if you just take a window and looked at how fast you were driving, you may be driving at different rates, like we kind of see in the graph there. You know, at one point 2.96, at one point we're driving 2.09, at one point we're driving like 1.48. But if you average out over the entire trip, from like the beginning of the trip to the end of the trip, and you followed sort of how fast you were driving, on average, maybe you were only driving 70 miles per hour. And that's what we look at in terms of rates of reaction. A lot of times we look at sort of the overall reaction, kind of from beginning to end, as the average rate that's happening. Again, if you sort of zoomed in on just like a pocket window of time, you know, you may be going a lot faster, right? And another pocket time, you may be going a lot slower. Also, like, you know, if you're running a race or something like that, right? Maybe at the start of the race, you're right out of the gates really fast, you're running really, really fast. Maybe towards the end of the race, you're a little bit more tired, right? So you're maybe not running as fast in that little window of time in the last mile of the race there than you were in the first mile of the race. But again, if you average out your whole sort of race, you run at a particular rate, average rate for the entire race. And so for our average rate here, we take for BR2, which again is a reactant, we have our minus here. And again, we take basically our final concentration minus our initial concentration. And because again, this is going to always yield us, because this is a reactant, a negative number on top. That again is why we have our negative here. Negative, negative should always turn your average rate into a positive value when you calculate it. Any questions on that there? All right, we will lay it up there and